Now we see how to find the equation of a plane passing through three given non-collinear points. Right? So let us imagine that there is a plane and we are given three non-collinear points. Let us call them as A, B and C with their position vectors as A bar, B bar and C bar respectively. Okay. So of course these are required to be non-collinear, because if they are collinear then there will be infinitely many planes passing through them. Alright. So as usual we consider some generic point P with position vector R bar in the plane. Okay. Now to develop the equation of the plane, what do is we join point A with the remaining 3 points. Okay, so therefore we get three different vectors. The first one is AP bar, second vector is AB bar and third vector is AC bar. Now if you look at these three vectors, they are all coplanar because they all lie in the same plane. So therefore if we take their scalar triple product, then that must be equal to 0, because we know that for three coplanar vectors their scalar triple product is 0. Now we simply describe these vectors. So AP bar is nothing but R bar minus A bar dot AB bar is B bar minus A bar cross AC bar is C bar minus A bar equal to 0. So we will of course expand this and get the final result, but the easier approach to directly get the equation is, if you look at these three vectors which are present in the scalar triple product, you know that a scalar triple product is given or calculated as a determinant in which the first row is the coefficients of the first vector, so that is R minus A bar stands for X minus X1, Y minus Y1 and Z minus Z1, because the general point stands for XYZ as the coordinates. The first given point stands for X1, Y1, Z1, and similarly the other 2 points will also be taken as with their respective coordinates. So now in the second row we have B bar minus A bar, so that means we will be subtracting first from the second, so it is X2 minus X1, Y2 minus Y1, Z2 minus Z1, and lastly we have third minus first, so it is X3 minus X1, Y3 minus Y1 and Z3 minus Z1, and this is equal to 0. So therefore the first form is easier to be remembered as a vector form, whereas the last equation in terms of determinants is the Cartesian form as required. Now based on this we can derive another form that is also called as the intercept form of the equation of the plane. Let us see how it can be derived. Suppose that there is a plane which intersects the x, y and z axis in three different points. Okay, so let us consider a most general case. So here we are showing the points where it is intersecting x, y and z plane. Okay. Let us assume that the point where it intersects the x-axis has coordinates a, 0, 0. Clearly its y and z coordinates will be 0 because the point lies on the x-axis. Similarly, let the other point on y-axis be 0, b 0, and the third point on the z-axis be 0, 0 and c. So a, b and c are called as the intercepts. So in other words, we have obtained three different points through which the required plane must be passing through. So therefore clearly we write the equation of the plane using the 3-point form which we have just derived some time ago, right? So on using that and simplifying, we get the final equation as x upon a plus y upon b plus z upon c is equal to 1. So that's the simple Cartesian form of equation of the plane using the intercepts. Okay, so isn't this very much analogous to the double intercept form in case of a line in two-dimensional plane that we have studied earlier? Okay, so it is just an additional term in the third dimension, so the z term is extra, which indicates a plane. Right, let's go ahead and solve one example. find the equation of plane passing through these three given points. So since we are given three different points, let us go ahead and use the Cartesian form. So x minus x1, then y minus y1 and z minus z1. See, we are going to subtract these values from x, y, z. Then in the second row we have x2 minus x1, so that is 0 minus 1, then y2 minus y1 and then z2 minus z1. And lastly we have x3 minus x1, so therefore that is minus 1, minus 1, 4 minus 1 and minus 2 minus 3. This whole thing is equal to 0. So therefore let us simplify that. We have x minus 1, y minus 1, z minus 3 as it is. Minus 1, 0, minus 1, minus 2, 3 and minus 5 equal to 0. Let's simplify that further. So therefore x minus 1 into bracket we have 3, then minus y minus 1 into bracket we have 5 minus 2, that is once again 3, and last term is z minus 3 into bracket minus 3 is equal to 0. So clearly here itself we can cancel out a factor of 3 and therefore we'll get x minus 1 minus y plus 1, and this minus will flip the terms, so we'll have minus z plus 3 equal to 0. So therefore lastly we get, collecting all the variable terms, so x minus y minus z, minus 1 and plus 1 cancels, we have plus 3 equal to 0. That's the Cartesian equation of the required plane.